So hi, everybody. It's wonderful to see all of you. And today I would like to tell you of a work that we posted about a month ago titled The Regularized Phase Volume of the Three-Body Problem. And now I will share the presentation. Okay. Is it okay? Can you see?
Yeah.
Wonderful.
Yes, I can see.
Okay, so I think everybody knows me, and I call this meeting a three-body seminar. We have here people from around the globe with three-body interests, but mostly with some Israeli and or American connection. And it's based on work with Yogesh Dandekar, who was a postdoc in my group and recently received a faculty position in India, in Pune. And myself, Lederer, who was an undergraduate, and it was his undergraduate project, and Shubhajit Mazumdar, who was a postdoc with us and now is a postdoc in Seoul, and he is attending us. It's also related to previous works on the three-body problem. The first one here is the statistical theory, the flux-based statistical theory. The third one is a natural dynamical reduction. And the middle one is a test of the above, of the statistical theory above. We'll see as we go along how these things are related. So the outline of the talk is going to be, we'll start with the introduction and with the definition of our goal and jump directly to the results. So everyone should know what the results are. And then I hope we will have time to discuss the derivation, and the derivation will have two ingredients. First, we will define the regularization. The regularization will, this definition will require some care. We'll identify the divergence of the naive quantity, and we will discuss the reference quantity that needs to be subtracted and the regularization scheme. And then we will evaluate this regularized phase volume, and that will be divided into analytic integration over some variables and numerical integration over the rest, and presentation of the results or repeating the results. And finally, we'll have a discussion. So introduction and goal. So the three-body problem needs no introduction here. We are discussing three-point particles moving under the influence of a Newtonian force of gravitation, and it can be described. So the parameters are the masses, initial conditions are positions and velocities, and it can be described by the following Hamiltonian. And this work is really a follow-up on a recent statistical theory that we call the flux-based statistical theory. And here I would like to mention recent works on other statistical theories by Stone and Lee, and Stone is with us, and by Ginat and Peretz, and I believe Ginat is with us. And all of these are non-hierarchical systems. Yes?
Also Chagai is here.
Oh, wonderful. So also Chagai Peretz is with us, wonderful. Thank you. And for completeness, I will also mention that even these are non-hierarchical systems. There are interesting non-integrable chaotic issues also in the hierarchical limit. And this is a limit where Smadar Naoz, who is with us, and Chagai Peretz did a lot of work. So what do we need from the flux-based statistical theory? We will throughout assume that the total energy is negative, therefore the system cannot disintegrate into three particles, only into a binary and a third. And we'll collectively denote the outcome parameters by U. So that would be the direction of the escaper, the velocity of the escaper, the binary parameters, the identity of the escaper, which one of the three, and so on. And the main relation, the main result of the flux-based statistical theory is the outcome distribution given by this simple expression, which I will now explain. the first term, d gamma, is the decay rate or probability per time. Actually, it's the differential decay rate. That's why we have here a differential per unit of outcome parameters du. And that is written in a factorized form. Emissivity of u is a function which we so far know not much about. And the asymptotic flux is known in closed form. So in this way, we reduce it. Instead of having to find d gamma, then we only need to find the emissivity where the asymptotic flux is already known. So in this sense, it is a reduction. And we have here a prefactor, 1 over sigma bar chi, 1 over sigma bar chaotic. And that's the subject of the current paper. So we call that the regularized chaotic phase volume given the conserved charges E and L. It serves as the normalization of the decay rate. If you like, it sets the scale, the overall time that it takes for the system to decay. Okay, so we will want to study this, well, more precisely a variant of it, as we'll see in a moment. So we are after this normalization, which sets the time scale for decay. Oh, okay. So how shall we regularize this sigma chi of E and L? Well, it's, as we'll see in a moment, it is divergent, and we'll start with a quantity which is a bit easier, and it's sigma of E alone. So we will look at the phase space volume of the system, accounting for conservation of angular momentum and center of mass, and for energy, but not accounting for angular momentum. Okay, so this is just sigma as a function of E and not of L. So it's somewhat a simpler quantity, but it also diverges, and this will be the subject of this talk. In future work, we will find sigma bar of E and L. So we'll have to distribute the current quantity over all possible values of L. And this quantity is close, I will not discuss why, to the chaotic one. So we will approximate it, and that should allow us to compare with simulations. So currently, we won't be able to compare with simulations, but we have a well-defined quantity, if you like, mathematically or theoretically defined, and we wish to define and evaluate, well, we also need a precise definition, actually. So a precise definition and evaluation of this regularized phase volume as a function of E. I have to mention that the word regularized is sometimes used in several meanings in the three-body literature. Sometimes we use it when we want to remove singularities associated with collisions. This is not the meaning that we're going to use here. Here we're going to use the meaning that we have a quantity which is naively divergent, as we often have in quantum field theory, and we're going to find a finite version of it. Okay, so we'll take something which at first appears to be infinite, and we'll define out of it a finite piece in a well-defined way. Okay, so as promised, we'll jump directly to the results. I'll show you the chosen definition, full definition, and the evaluated quantities. So the definition is going to be that the regularized part will be equal to the bare part minus a reference part. I hope you can see my cursor. It should be, yes, wonderful. Whereas each one of them is positive by definition, the regularized part, which is a difference of 2, is not necessarily positive. However, for the theory to make sense, we expect it to be positive, and we'll see that for most values of the mass, it will indeed be positive, but for some values of the mass, it will be negative, and that would have a special interpretation, but we'll see that later. Okay, so the positivity of the regularized value is an issue. Now I have to tell you what is the reference quantity, and the reference quantity is going to be very similar. It's going to be a phase volume, an integral over all of phase space with delta functions for linear momentum and center of mass. but the Hamiltonian function is going to be different. Instead of the original Hamiltonian, we're going to use the effective Hamiltonian, where we have a binary energy and an energy between the binary and the escaper divided by the distance between the binary and the escaper. So this is shown in this figure. You see that we have here an escaper or a tertiary, which is far away from the binary. Here is the binary. And we replace the binary by its total mass at the binary center of mass. And then Rf is this distance between the tertiary and the center of mass of the binary. So when the binary is far away from the tertiary, this effective potential is a very good approximation for the full potential. And this is the reference system and reference phase volume that we're going to use. Moreover, we will have to define the region in phase space that we integrate over, and it's going to be given by this condition that the binary energy is bounded by the total energy divided by 2. We'll discuss that later. And we have 3 of these reference terms, or well, the reference term is the sum of 3 terms, or sometimes it's called the counter term, each one corresponding to each possible identity of the escaper. Okay, so this gives us a full definition of what we're going to compute. And now for the results of the evaluation. Well, first, in order to explain the evaluation, we need to understand, I need to tell you that the full quantity, its dependence on the energy and the masses can be factored out such that the only remaining dependence is on alphas. The alphas are the potential strength constants. So V is equal to alpha over R. In our case, alpha depends on M. So let's say alpha 1, 2 is G, M1, M2, okay? But we pretend here that alpha could be more general. So in this way, we separate out the dependence on the masses and the dependence on the energy, and the only non-trivial part is the dependence on the potential strength constants, the alphas. So what is M3 and M? M is the total mass. M3 is the product of all 3 masses. Sigma 0 is the following expression in the alphas, and it is chosen such that sigma hat will be dimensionless. Okay? So in this way, I just need to tell you what is sigma hat. We don't need, the rest is already fixed. So now what is sigma hat? Well, before showing you sigma hat, I want to illustrate how the regularization works. So I will show you the density of sigma distributed over geometry space. Geometry space is a 3-dimensional space of triangles. Well, if you have 3 points in the plane, then you have 6 coordinates. But up to translations, only 4 remain. And up to rotations, only 3 remain. So the space of all possible triangles up to rotations and translations is 3-dimensional, and we have a very specific way of defining it. Unless somebody asks me, I will not discuss it. It's discussed in detail in the dynamical reduction paper. I will just show you how the surface of constant potential energy looks like. It looks like a joint pipe, a joint of 3 pipes. And for fixed energy, the particle representing the system can only move within this pipe, where each asymptotic pipe represents a hierarchical configuration. And since there are 3 possible hierarchical configurations corresponding to either 1, 2, or 3 being far away from the other 2, then we have 3 pipes, and the intermediate region, or the joint itself, is the place where all 3 bodies are in comparable distances, okay? Whereas the pipe is something like this, where one of them is far away. So that's going outside in the pipe. I hope this was clear enough. Let me show you the illustration of the regularization. So here we take some cross section through the pipe. You can see that we have these 3 pipes colliding, And I plot here the density of sigma. And you can see that this density is constant as we go out. So it's very clear that as I'm going to integrate this with a proper measure, then the integral is going to be infinite. Okay, so the total phase volume is going to be infinite. Now, we plot here the reference quantity, which is really a sum of three terms. So really a sum of three terms, each one describing roughly a pipe that ends somewhere in the middle. And you see that far away, it looks very much like the bare one, but in the center, it looks somewhat different. And when we subtract the two, this gives us the density of sigma bar, the regularized sigma. You see that very little remains in the asymptotic pipes, and the only difference is in the middle. The scale here is zoomed in relative to those scales. Okay, so you can see with your eyes how the regularization works, how the reference term approximates the bare term very well outside in the asymptotic pipes, and the only remaining difference describes these non-hierarchical configurations. So this is an illustration, and now let's go on to the results. Here are the results. So we're going to plot the value of this sigma head as a function of the three masses. The three masses imply the three alphas, so it's the same. We set M3 to be 1, and we have here M1 smaller than M2, smaller than M3 equals to 1. So we have here a contour map of the values of sigma hat. And we've highlighted sigma hat equals to 0. So to the right, it is positive, and to the left, it is negative. So we see that something wrong goes and sigma hat becomes negative when M1 is very small. M1 being small is a very natural limit. It's the test mass limit. Okay, so in this test mass limit, where we expect that that we should not be able to use the same statistical theory. In the test mass limit, we should use a theory with fewer degrees of freedom. It is still chaotic, but it is a different theory. So this theory shouldn't work there, and indeed it doesn't. Okay, so we ran a few tests for these results. The first test is that we get finite results. We start with an infinite quantity, but after we subtract, we get finite results. So that's great. The second test is, well, I'll explain it more later, but we computed it in two different ways, using two different expressions for the reference term. And they are quite different. You integrate on quite different integrands, but the result, the numerical result, is equal as it should be. So these two different ways are a good test. And the positivity issue that makes sense is also a test. Skin dependence, well, we'll discuss that.
Can I ask a question?
Yes, please. Wonderful.
So you have, from the sigma equal 0 line that you have there, that separates between when the approximation holds,
yes.
You have a specific mass ratio for which the behavior breaks, right? You can get that from the line, right?
Well, yes, the line tells you what are the values of M1 and M2 where it happens. It's not clear whether it's a numerical fluke and whether the line should go all the way down or not. But I'm not sure if you refer to that. But you can see that the whole region, or almost the whole region of M1 being small, is excluded.
So I guess my question is how small, right? So
so here you have a specific value. You see,
yes.
You can see, for instance, over here, M1 there is about 0.115, and 0.115 is relative to M3. Okay.
I guess my surprise is that it's almost constant with M1. So that's right. It's almost right because, as you say,
right.
0.1.
Right.
in, and it's almost vertical.
Right. So you can see that.
I wonder if you understand that.
No, we have no. It's one of the interesting questions that come out of this. We see that M1 at most here is below 0.2. So that means that if M1 is above 0.2 of M3, then we're in the statistical theory is still working. Okay, we're in the regime of validity of the statistical theory of the non-hierarchical system. Okay,
Barak?
Yes, please.
Just to follow up on that, I mean, would it be fair to say that the statistical theory is probably breaking down a little bit to the right of this black line, since sigma is in the denominator of d gamma? This is telling you that you're getting like a divergent disintegration or escape rate as you approach from the right. So would it be fair? Am I interpreting that correctly, or have I misunderstood?
Yes. Thank you, Nick, for the question. Yes, this is absolutely correct. The way the theory fails is that the volume inside our leaky container, so we have some analogy with the leaky container, and in this limit, it's as if the leaky container has no volume, only holes, okay? So of course, the theory holds well when the holes are small, right, compared to the volume of the container. And when the volume of the container is small, then already somewhat before it, the theory fails. But in order to, I want to go to the next point because it will reflect on both your question and Smadar's, and that of scheme dependence. There is some freedom in our definition of this sigma bar. We'll discuss it later. However, this freedom, as we'll discuss, can only shift these results by an overall additive constant. So I cannot claim that these values are completely natural. If you shift them by some value, I don't know, by 5, by 10, that would shift somewhat the zero, you see? So this zero, I do not consider to be completely natural. It depends also on some conventions, more precisely on what you consider to be a sub-escape excursion. So we'll see that later. So that reflects on the definition of the regularized sigma, the definition of the precise definition of when we identify a sub-escape excursion, the situation where one body is thrown far away and then falls back. And that can shift the zero by somewhat, okay? Okay, great. Okay, we discussed the breakdown in the test mass limit. And of course, this is the first evaluation of a regularized phase volume for the three-body problem. Okay, so we can stress that. So these are the results. And now I'm going to proceed to the elements of the derivation. But if there are any further questions about the results, the two results, how we chose to define the reference term and the subtraction, and what we get for the values, then it's a good time now.
I had one question, although it's possible we'll get to this in the derivation. Okay. You mentioned that you integrate over up to binary energies that are half the total energy of the system.
Right.
Is there a physical motivation for that? It seems like it's excluding energetically possible outcomes where, for example, the binary gets 99% of the energy and the escaper leaves on a nearly parabolic orbit. Or exactly. should I understand this as like a mathematical convenience?
No, it's not a mathematical convenience. I will try to argue that it's very physical, although the precise value is somewhat arbitrary. And that has to do with this scheme dependence or regularization scheme dependence that I mentioned. So instead of taking half E, you could have taken 0.4 E or 0.6 E. That would be equally reasonable. And that would shift the results by an additive constant. Okay, so we'll get there. That's an important point.
Sorry, can I ask another quick question?
Please.
So it's related to Nick's question. So EB in your definition is negative. Is it defined such that it's negative? Or
yes. So we take EB and E to be negative. I wasn't sure whether Nick was using these conventions.
So it goes all the way to minus infinity, essentially. So right.
Right. So we forbid large binaries. We don't forbid tight binaries. We forbid large binaries.
Right. In the reference definition.
In the definition of the reference. Exactly.
Okay. Thank you.
We'll see why. Okay. Let's go on, and many these things will be discussed. Okay.
Thank you.
Okay. So we go on. Thank you for the question. So derivation. The derivation will have two chapters. The first one is the definition of the regularization. So the first thing we need to do is to identify the divergence and the cause of the divergence. So here is again the expression for sigma of E with this delta function for the energy equal E. And the divergence comes from hierarchical configurations where we have a tertiary far away from a binary. In this case, the potential, which is a sum of three terms, can be approximated very well as a sum of two terms. Actually, the binary energy is the largest, but then there's also the effective energy between the binary and the tertiary, and we should account for that as well. We'll see later more precisely why. So V, for very large RF, V is asymptotically independent of RF. So that has to do with going asymptotically in these pipes that we saw before. And that's why the integral will be an integral over these RFs times some finite quantity. But if we have a finite integrand over an integral like this, then of course it diverges like the volume of RF or RF cube, where RF again is the separation between the center of mass of the binary and the tertiary. Okay, so this is the kind of divergence, and we see that it is very well approximated by the effective system since we are in a hierarchical configuration. So we can approximate V by VF. Now, before we go on, I want to recall the relation between phase volume, more precisely sigma of E, this phase volume for given energy, with scattering time. So this is something that was mentioned already in the first paper. So in one dimension, consider a Hamiltonian of a particle moving under the influence of some potential. You can have in mind this potential, and here is a particle with some energy E. And we want to compute sigma of E. By definition, it's integral dp dx over the phase volume times the delta function for the energy. We can perform the integral over P against the delta function. And by the rules of delta function integrations, we need to divide by the HDP, and we need to evaluate it at the two solutions of P equals plus minus PV, where PV is the square root of the available energy, E minus V of X. Now, what is the HDP? The HDP, if we look at the Hamiltonian, is nothing but P over M, which is V. Oh, and here, by the way, I'm taking just the sigma of particle moving from the left to the right. There's also another sigma for particle moving from the right to the left. It will just double the value, so it's enough to concentrate just on one of these values, P equals plus PV. Okay, here I'm taking P equals plus PV. Now we recognize that what we're integrating over dx over V is nothing but an integral dt. Okay, this is high school physics, right? So what does it mean? It means that the sigma of E is nothing but the total time that it takes the particle to traverse from left to right. And of course, this time is infinite. It's true, it slows down a bit here, and then it accelerates again, but it takes an infinite time. So this is the divergence of sigma in this one-dimensional example. But here, it is clear how to regularize, or pretty clear. What we should do is we take a reference particle, the red particle, and the red particle doesn't feel the potential at all. So they start together at infinity, but then the blue particle gets slowed down because of the repelling potential or stopping potential, while the red one continues. And after they cross the potential, they again have the same speed, but they're separated by some finite time known as the delay time or scattering time. And mathematically, it's given by a similar expression, only we need to subtract a term that is similar to the previous term, PV, but P0 has no potential. Okay? So this is the definition of a regularization of a scattering time. And since scattering time and sigma of E are the same, then we can also take it to be a regularization of sigma of E. So we can define sigma bar of E to be an integral dp dx of delta of H minus E, the original H over here, but subtracting a delta function for H0, where H0 only has a kinetic term, but no potential. So H describes the blue particle in this figure, while H0 describes the red particle. Okay, so there is a relation between scattering time and sigma, which we will have in the back of our mind. The generalization for more than 1 degree of freedom is that sigma of E is not the scattering time, but the integral over all asymptotic states of the scattering time. So in one dimension, there is only one asymptotic state, or a discrete number of asymptotic states given the energy. Either it goes from left to right or from right to left, or actually two, but discrete number. In higher, if we have more degrees of freedom, then we have various incoming particles, and we need to integrate over their scattering time, and that would give us sigma of E. Now we want to go back to the three-body problem. And we want to ask what is going to be our H0? What is going to be the case where the Hamiltonian or the potential when we turn off the interaction potential? So let's go slowly. First of all, we're scattering a tertiary of a bound binary. So in order to account for the fact that the binary is bound, we should certainly take into account the binary potential energy. But this is not enough. If we only do that, we will find that we have a divergent. T scattering is still divergent. This is a well-known, it's known as the Keplerian divergence. And in order to avoid that, we also have to take into account this other term, which describes the faraway interaction of the binary with the tertiary. So altogether, we got that our reference potential is nothing but this effective potential, which has the binary term and the binary tertiary term. Okay, so this tells us that we should use as our reference system this effective approximation that the potential has two terms instead of three. But we should still be careful, or we should still define the domain in phase space over which we integrate. So it's already clear that sigma reference is going to be sum over the three possible escapers, integration over all phase space variables. Here I wrote them as RB and RF, the binary distance and the distance to the effective distance. So it's equivalent to the previous expression that we had with the integrating over all R's and all P's and delta functions for PCM and RCM. But the delta function here is for the effective Hamiltonian with two terms in the potentials, not with three. So now we're after this domain. And this is where this condition will come. So let's see how it works. So our intuition about the scattering time tells us that we want to remove from the phase space domain the parts which describe asymptotic motion segment. So we have a binary and a tertiary, and the tertiary comes in and then starts some free body motion, and then it gets emitted for good. And in the middle, there are also some possibly subescape excursions where one of them goes far away and returns, and another one goes far away and returns. So we first want to remove these asymptotic motion segments. And for the asymptotic motion segments, necessarily, of course, the effective energy is positive. So that's here I mean by that, the energy only in the relative motion. So of course, the relative motion in an open trajectory, both the potential and kinetic, is positive if and only if it's an hyperbola or a scattering trajectory. So we need to remove this. However, this is not enough, it turns out. And that's why it took us some time. So this under-regulates. The difference is still infinite if we just take that. And that's related to the fact that in the three-body problem, the average scattering time is infinite. That was noticed already in 83. And the reason for that is the long subescape excursions. They can add a lot of time to the scattering time. So we should also remove these excursions. And it also makes sense because we wanted to remove all the regular parts of the motion. We wanted only the chaotic phase volume. So these excursions are regular motion. So we need to remove them anyway. So we have to remove them in order to get a finite result, and we have to remove them because they're regular and not chaotic. So we still need to do that, to remove them. So how do we do that? So we need to remove excursions. And an excursion is identified by two criteria. First, we want a hierarchy of distances. We want a tertiary to be far away from the binary. That's the second condition. And we also want the binary to be bound. So we have two conditions that define an excursion. Now we're going to alter a bit the second condition. So the first difference is we're going to say we're going to have this reference term be nice, we're going to remove complete orbits, not only when the tertiary is far away, but also when it's close. So we'll move a full ellipse. So that tells us that actually we want to take that the semi-major axis of the binary system is much smaller than the semi-major axis of the effective or relative motion. However, here, we will find out that the reference term is not proportional to this sigma zero that we defined before. I think I don't have time to discuss it in detail, but I will say something about it in a moment. So I change it, and instead of taking AB, I take alpha over A or A over alpha. So when we do that, and when we state the condition that alpha over A B is going to be larger now than alpha F over AF, then we will get a reference term that is minimal in the sense that it will be proportional to sigma zero. And this gives us the condition that EB is smaller than some constant of order unity times EF. And now we're going to make this arbitrary choice that Nick alluded to before, and we're going to say simply EB smaller or equal than EF. So we take this order 1 constant to be simply 1. That's the most symmetrical choice, but there is nothing truly natural about it, I would say. And remembering that EB plus EF is E, then this is equivalent to saying that EB is smaller than E over 2. Okay, so if this is E over 2, EB is smaller than E over 2, and EF is larger than E over 2. So EF can be either positive and describing open trajectories, or there is a range of negative EFs which describes excursions, which describe bound orbits. And we want to remove both of these. And here I'm using all the time this relation with the scattering time. So I'm actually removing parts of of trajectories which correspond to the regular parts or the asymptotic parts. Okay, so Nick, this is the explanation that I have for this phenomena. Let's see. Well, here I have some explanation why the divergent part of the bare sigma is proportional to sigma 0. I will skip it. And I will say that the reference term also has singularities. Actually, it has 6 singularities. 3 of the wanted type, where the binary is far away from the tertiary. And this extra condition doesn't change that. So it will not change the nice cancellation that we wanted. However, the reference term also has something that we call a spurious singularity. And a spurious singularity happens when the tertiary is at a fixed distance from the center of mass of the binary. So you see, we have here a very large binary of blue and red, and it's a very large binary, but its center of mass happens to be close to the tertiary. Physically, the potential is not very large, but because of this term that takes the potential between the tertiary and the center of mass, we get a rather large one in the effective. So in this case, the effective potential does not approximate well the full potential, and we want to get rid of it. And this is exactly what this condition on EB does. It forbids these large binaries, and it excludes them from the integration over the reference. So in this way, we don't get, in the reference term, additional singularities that we didn't have in the bare quantity. So here I have a summary of everything again. We have here the expression of the definition and expression of sigma bar as a difference of the bare quantity minus the reference quantity. The reference quantity is a sum over the 3 escapers of the effective potential, where the effective potential is given by these 2 terms, a binary one and a relative one. So this concludes the discussion of this extra condition. So Nick or anybody else, if you have a question about it, this would be a good time.
Yes, I have a question.
Yes.
Why do you take this limit on EB even when EF is larger than 0? Like even when it's a hyperbolic trajectory, then we know that it's not an excursion.
Good. So thank you, Dina, for the question. So let's go back. Okay, here is this condition. EB is smaller than E over 2. So you say, what happens if EF is positive? If EF is positive, and I'm now trying to show you with my hands the energy axis, this would be the 0, and this would be total E. And now if EF is positive, that means that EB is below E, right? Because the sum of them has to be E, and EF is positive. So EB is below E. Therefore, it's for sure below E over 2. So in the case that you mentioned, indeed, the condition is meaningless. It is satisfied automatically.
Okay, yeah, thanks.
I can do it again with paper.
No, it's okay.
Are you sure?
Yeah.
Okay. Okay, so the point is that in the case that you mentioned, as you intuitively guessed correctly, the extra condition doesn't change anything.
Thank you.
Okay. Okay, great. Okay, so now we go into, after we've defined, there's still something that we need to discuss in the definition, sorry. So
Barak?
what are the, yes, question?
So sorry, I did have one extra question before we move
Yes.
on. It's not obvious to me how unique this regularization scheme is. So I take your point about this choice of EB over 2 for the sub-escape excursions. I take your point about that producing an additive constant. But it seems like in principle, you could add non-divergent functions of E to sigma ref and still regularize the phase volume, but there would be many new free parameters that could enter the problem. I see the sort of naturalness of this motivation, especially with your one-dimensional analogy, but is there some stronger argument about why this is the preferred regularization scheme?
Wonderful. You're absolutely correct. It's a great question. The next transparency addresses it partially. Okay. So this is the transparency that I forgot. So what are the properties of the reference term that we defined, and what is the remaining freedom? So it is physically motivated. We gave this motivation of the relation with the scattering time and wanting to take out the asymptotic parts and the regular excursions out. It does the job, it regularizes, but it's also proportional to this expression sigma zero, this expression that was a function of the alphas that goes like alpha to the 6th. Since the divergence is proportional to sigma zero, I argue, then this is the minimal kind of counter term or reference term that you can have, one which is proportional to sigma zero. You could have additional pieces, and that would not only take care of the infinite part, but also shift the value, the finite value. So you could do that, but there is some minimal family of regularization schemes which are all proportional to sigma zero. And if we use only this minimal family, then our results are defined up to an additive constant, as long as we don't have an argument why this specific scheme is the natural scheme, then we have a freedom of this additive constant. However, if you want to go outside of this family of reference terms, which are not only proportional to sigma zero, you could do that and you would get regularized values, but I would call that non-minimal, okay? So that's what I can add to your question.
Okay, thanks.
In here, alternative schemes and normalization. So as long as we choose, since the divergent part of bare sigma is proportional to this sigma zero, then we consider minimal class of references, which is proportional to sigma zero. This can do the job. And once we define sigma hat to be the difference divided by sigma zero, then we have this property, as you see, that the change of scheme shifts sigma hat only by an additive constant. So sigma hat is a function of the alphas or the masses, and it's shifted only by an overall constant, which is independent of the alphas or the masses. Okay, great. So here I concluded the part of defining the regularization, and now I go on to the evaluation. And okay, we'll have to go somewhat quick through it. So here is the initial expression. We're going to be able to perform some of the integrals analytically. And the fact that some of them are possible to do analytically, that gave us the idea that there is some dynamical reduction that we explored in full in the dynamical reduction paper. So it's not a coincidence that you can do some of these integrals. So the first integral that we can do is over all the momentum variables, since the energy depends quadratically on the momentum. And we get this m3 over m to the 3/2. I remind you that m3 was a product of all masses and m was the sum of all masses. And we're left only with a space integral or configuration space integral over this quantity and plus squared. The plus is the ramp function, which is a kind of cutoff. If the argument is negative, then you get 0. So you integrate only when these values are positive. Okay, this is the definition of the ramp function. X plus for positive x is just x, but for negative x, it gets cut away. It's 0. And the derivation is interesting. It was discussed in Flux-Based. We introduced some auxiliary conjugate variables. They can also be thought as kind of classical ghost, if you like. They can be thought also as some kind of analogy with Schwinger parameters, but I will not go in depth. Let's proceed. The energy dependence can be factored out by dimensional analysis. Again, I will do it quickly, but this dependence on e to the 4 comes out. And what we have left here is -1 minus v, or this is v over e, actually. Now, there is an interesting integration that we can do over the overall scale of the configuration. So we take a specific triangle and we rescale it. Okay, what happens? It turns out, well, it's nothing but the simple integral here that I have here. So we have v bar over r minus 1 plus squared. Again, I'm going quick, but the result is interesting, and actually it has a very nice mathematical interpretation. The remaining integral is over the projective configuration space. So if the configuration space is 6-dimensional of all possible triangles, then after integrating over scale, we're left with a so-called projective integral where v to the 6th, since v goes like 1 over r, the potential always goes like 1 over r because all the terms in it go like 1 over r, both the bare and the reference. So v to the 6th goes like 1 over r to the 6th. And since we have a 6-dimensional space that we're projectivizing, this is exactly the correct weight or correct dimension. So again, if someone asks me, I will go into more detail, but let's just say that it's possible to carry out this integral. Next, we can take care of the orientation of this triangle, which represents the configuration. So any 3 points define a plane and a triangle in this plane. So first we have the orientation of this plane, and that contributes a factor of 4 pi over 2 because there are 4 pi directions for a plane, the normal to the plane, but actually the normal to the plane can go in either direction. So I have to divide by 2 times delta, where delta is what comes out of the Jacobian of the change of variables. It's actually related, interestingly, to the triangle area. It's twice the triangle area. And we have rotations within the plane. So after we fix the plane, we have different triangles that are related by rotations. So we have here an integral of 2 pi of this rotation angle. And after we combine all these integrals, we finally get the following result, where the remaining integral is over theta and phi, which parameterize something that we call the shape sphere. And you see here a remnant of this v to the 6th. You see sum of 3 terms, alpha a divided by something which actually represents a distance. And there are some normalization factors. So this theta and phi are part of a shape sphere. This is a term coined by Meckel and Montgomery in 2013, but something equivalent was already defined by the great Lemaitre in the 50s. And its definition of the shape sphere, it's a unit sphere in geometry space. So that means we consider all triangles shapes up to size. So actually it's all shapes. Yes, all possible 3 angles. And this is a very nice way to represent all possible triangles, not only up to translation and rotation, but also up to rescaling or similarity. And there are some interesting points on this sphere. The uppermost point is the equilateral triangle, the right-handed one. The lowest pole is the left-handed equilateral triangle, or the one with opposite handedness or orientation, opposite orientation. The equator represents collinear configurations. And out of these collinear configurations, there are 3 special points of coincidence. So for instance, C1 is the point where M2 and M3 are coincident or collide. C2 is the point where M1 and M3 collide. And the other points on the equator are points where the 3 are collinear, but none collide. Okay, so this is again very fast, but a description of the remaining integral or the geometric interpretation of this theta and phi as angles on this sphere of shape of triangles. Oh, there is a redundant P here, right? Because of the sphere, never mind. Okay. There's also a direct and explicit definition of theta and phi, which I can skip. We can do the counting of the variables. So we started with 9 degrees of freedom or 18 phase-space variables, but we had 7 delta functions for PCM, for RCM, 3 each, and for energy. And then we were able to integrate over momenta, over a planar reduction. Then we had the scaling, the rotation angle, and finally we're left with the 2. So this is a budget of variables. So we're left with 2 integrals and no delta functions finally to integrate. We're not done yet. We have to repeat the same thing now for the reference expression. And what we get is some compensator plus this integral again over theta and phi. And this time the domain is split into 2 parts. I'm going fast over it, but if someone will ask a question, I will discuss it. Okay, so now we should subtract the 2 at the level of the integrands over the sphere and integrate over the sphere. And this is indeed what we do. So now we proceed to the other part, the numerical integration. This was done using the n-integrate command in Mathematica. There are 6 singular points which I described, but the integral converges there. So it happens that we have, like 1 over square root of x dx. There are integrals which are singular, but the integral converges there, and this is exactly what we have here. Numerically, this is a sensitive point, but the n-integrate routine of Mathematica is pretty smart, and it knew how to handle these convergent singularities, both the wanted and the spurious. And I think the next step should be the results. Okay, so here again, I repeat the results. So I show you again the density of sigma, of bare sigma, the density of the reference, and the density of the difference of the regularized quantity. So now you can appreciate it better after having gone through the elements of the derivation. And I want to show you again the plot of sigma hat. So I hope you can appreciate more what went into it. And finally, we also did the same thing for the planar 3-body problem. We can define a planar 3-body problem. It's a different problem. All 3 points are confined to the plane. There are some similarities with the 3-dimensional one, but it's different. And for it, we get a different result. You see here the values of sigma hat. And here also you see something interesting. The values never reach 0, but there is a very steep slope in the test mass limit as M1 goes to 0. So I think it's fair to say that the resolution here is not sufficient to determine whether we find a line of sigma bar equals to 0 in the planar case or we don't, because of this very steep slope that we didn't further explore. It could be interesting to zoom into this area that Esmadar was asking about in the 3-dimensional case, and then we might be able to see with better confidence whether we actually reach 0 or we don't. And similarly, it may tell us that we probably also expect a breakdown at negative values in the test mass limit also for the planar problem, but it's not fully clear from this level of computation that we carried out. Great. Okay, so a brief discussion and we're done. So we've supplied a full definition for the regularization, whereas the original paper had some elements of the definition. Here we have the full definition, and in particular, the definition of this domain of integration for the reference term. That was not fully defined in the Flux-Based paper. We evaluated sigma. Not only we evaluated, but we exhausted all of parameter space. So we've evaluated it for all possible values of the masses. Okay, and we have a contour map over parameter space. The results are consistent with the expected breakdown of the statistical theory in the test mass limit. So we said that and discussed that. And as I mentioned, the possibility to carry out the analytical integrations told us that something is hiding there, and that gave us a hint to go towards a natural dynamical reduction where we separate the motion of the system to a kind of a rigid or non-rigid body describing the plane of the triangle that is moving, and the motion in geometry space, which describes how the shape of the triangle is changing over time. So we divide the three-body problem into two problems: a point in geometry space and a non-rigid body, but it's a bit similar to a rigid body, and that was discussed in a different paper, and that paper is strongly related with this effort to compute the total phase volume. And as I mentioned, this is the first evaluation or definition and evaluation of a regularized phase volume. Open problems. So first of all, we would like to go to the next step and evaluate the regularized value, not only as a function of energy, but also as a function of angular momentum. And that should allow us a comparison with simulation data for the decay time of three-body systems. Another additional interesting thing would be to understand the analytical behavior in this test mass limit. If we understood that, we could compare it more quantitatively to the data, to the numerical data. So we can expect that in this limit, we might have an analytical theory or a theory that will capture the behavior there. And that will tell us some more about this interesting limit of the test mass limit. And we could also try forces which are different from the Newtonian force, other three-body problems, maybe. So I think, let's see. So I think we've shown the two main results, the full definition and the evaluation of sigma bar. And we hope that will be useful to us in completing the flux-based statistical theory to give us a theory for the scale or a theory for the decay time of three-body problems. Thank you very much for your attention. And of course, I'd be happy to answer any questions.